Okay, we are talking here about rotational kinematics, and as an introduction to rotational kinematics, we have to start talking about, defining our variables, just like we did with linear kinematics. First equation that we saw in the lesson was that theta is equal to the arc length over the radius. And this problem right here demonstrates that, or requires that knowledge. Synchronous satellites are put into orbit whose radius is that. If the angular separation of the two satellites is 2 degrees, find the arc length that separates them. So this is S, and this is theta. Okay, so, and we have R here. Now we can also call this theta 0 and theta final if you're thinking about sweeping out that arc length, and which would make this delta theta. But however you want to look at it, either way works. Okay, so we want to write down the things we know. So delta theta equals 2.00 degrees, but we have to have everything in radians. Because the radians are the SI unit. They are the unit of angle for which there's a solid mathematical foundation, and none of your calculations will work if it's not in radians. So we multiply by the conversion factor in that there are 2 pi radians for every 360 degrees. So in a circle, there are 360 degrees, or 2 pi radians. That's just something you'll have to know. So the angle is, I'll just call it 4.00 pi over 360 radians. Okay, and the radius is, well, we have the radius because we have well, it's given to us here. So that equals 4.23 times 10 to the 7th meters. So then we'd solve this equation for S, the arc length, equals R theta, equals 4.23 times 10 to the 7th meters times 4 pi, I should say that's 4.00, we have to be consistent, pi over 360 radians. So the arc length then equals 1.47 times 10 to the 6th meters. And note on units, you have meters times radians. Radians are a unit, but they're kind of unitless. Whenever you do mathematical operations on it, you're not going to include that into the final units here. So that's why meters times radians equals meters. It's a little crazy, but it's just like degrees. Degrees are the same way. By the way, a note about radians. If you forget this equation, one way to think about it is when R equals 1 meter, this is the unit circle, the arc length then equals 2 pi r, which just equals 2 pi. So theta must also equal 2 pi because theta equals S over R, so 2 pi radians equals 2 pi 1 meter equals 2 pi meters. Just something to think about. Our next example, an airplane is 18 kilometers away, it transits the moon. The moon subtends an angle of this. Find the distance traveled by the aircraft during this transit. Okay, so we have the moon here. The moon is very far away, but we don't care about the distance to the moon. All we care about is the arc length traveled by this plane. And the plane is some distance r away. This is theta. So we want the distance traveled. So theta equals S over R. S equals R theta. R equals 18.0 times 10 to the 3rd meters. And theta is 9.04 times 10 to the negative 3rd radians. So the path length traveled by the plane is 163 meters. Okay, so we've introduced that relation. Now we're going to start working some examples that deal more with kinematics. And first we have to define all of our variables. If you remember in class, and I believe it was chapter 2, one of the first lectures, the average velocity is equal to the change in position over change in time. And so now the average angular velocity, denoted with omega, is equal to change in angle over change in time. So let's find out what we want to find the average angular velocity, and we have 2 revolutions in the time of 1.9 seconds. I'll just write these things down. Time equals 1.90 seconds, and change in theta is 2 revolutions. Well, how many radians are there in a revolution? Well, 1 complete revolution is 1 trip around the circle, so that's 2 pi radians. So delta theta is equal to 4 pi radians. The average velocity omega is equal to change in theta over change in t. So that's 4 pi radians over 1.90 seconds. And that is equal to, oh, I made a mistake. And I did this in class too. The change in theta is clockwise. Remember, we defined that as the negative direction. So this must be negative. This must be negative. And your answer is negative 6.61 radians per second. Clockwise, negative. Same kind of stuff. We're dealing with the average angular velocity of Earth's motion, rotation about its axis, and revolution about the sun. I'm going to draw a line here. This is the A part of the problem. So delta theta, as the Earth rotates around its axis, 1 complete revolution is, well, we'll just say 1 revolution, which equals 2 pi radians. And delta t is 24 hours, and in 1 hour there's 3,600 seconds. So that means delta t is 8.64 times 10 to the 4th seconds. So the average angular velocity is delta theta over delta t, which is 2 pi radians over 8.64 times 10 to the 4th seconds. And that is 7.27 10 to the negative 5th radians per second. On part B, we're looking at the system of the Earth. Got the sun. The Earth going around the sun goes around 1 revolution. So just like before, 1 revolution equals 2 pi radians. And delta t now is equal to 365 days, because it's 1 year. And we know there in 1 day there is 8.64 times 10 to the 4th seconds. We know that from right here. So delta t then is 3.15 times 10 to the 7th seconds. The average acceleration omega then is equal to change in theta over change in t. which is equal to 2 pi radians over 3.15 times 10 to the 7th seconds. And all that is equal to 1.99 times 10 to the negative 7th radians per second. Okay, so why are these positive? Well, does that mean that the Earth is going counterclockwise around the Sun? Well, yeah, it is. And is the Earth rotating counterclockwise around its axis? Well, yeah, depending on which direction you look at it from. If you're looking at down on the North Pole, then let's see, yeah, it would be going counterclockwise. But if you're looking down upon the South Pole of the planet, it's going clockwise and it would be negative. And likewise, it depends on what plane, from which direction you're looking at the solar system, or the plane of the solar system. So it doesn't really matter here because it could be positive or negative. Okay, we're edging into edging in deeper into the rotational kinematics, and you may remember from linear kinematics that average acceleration equals change of velocity over change in time. And of course, instantaneous acceleration is equal to the derivative of velocity with respect to time, but we're not going to deal with that right now. So the average angular acceleration is equal to the change in omega over change in time, change in angular velocity with respect to time. So let's look at our problem here. As seen from the front of the engine, the fan blades are rotating with an angular speed of negative 110 radians per second. As the plane takes off, the angular velocity of the blades reaches negative 330 radians per second in some time delta t. Find the angular acceleration. Well, let's start writing our variables down. Final. Well, the initial theta we don't really know. Well, we can say is equal to 0. We don't know what the final is. The original initial velocity is negative 110 radians per second, and the final angular velocity is negative 330 radians per second. We don't know this, we're looking for it, and time equals 14 seconds. Well, from our definition of average angular acceleration, delta t, so that is omega f minus omega naught over delta t. The average angular acceleration is negative 330 radians per second minus negative 110 rad per second over 14 seconds. That means the average angular acceleration then is equal to negative 15.7 radians per second squared. Closed wire operates at an angular speed of 5.2 radians per second, and it starts from rest. So omega naught equals 0. Call this omega final. It reaches an operational speed with an average angular acceleration of 4.0 radians per second squared. That's alpha. How long does it take to reach operational speed? How long is asking for delta t. So, writing down our kinematic variables, we don't know anything about theta. We can say it starts at 0, but we don't know where it ends in the end. Omega 0 is equal to 0 because it's at rest. Omega final is equal to 5.2 radians per second. Alpha is equal to 4.0 radians per second squared. And time, we don't know that. We are looking for that. So we're going to use the kinematic equations. Let me just start by writing down what those kinematic equations are. Well, I guess the simplest one is AT, and x minus x0 equals v0 t equals v0 t plus 1/2 at squared. X minus x0 is equal to 1/2 v0 plus v times t. And finally, v squared equals v0 squared plus 2a delta x, or I should say, consistent. So these are our kinematic equations for linear situations, but we're dealing with rotational kinematics. So I'm going to take these same equations and just plug in, or replace them with rotational variables. So the analog of velocity is omega, angular velocity, equals original angular velocity, plus the analog of acceleration is rotational angular acceleration, that's alpha, and time is the same. The analog of position is the angle theta minus theta original equals the original velocity, so that's the original angular velocity here, times t plus 1/2 alpha t squared. And again, position is theta minus theta naught equals 1/2 omega naught plus omega times t. And finally, omega squared equals omega naught squared plus 2 alpha theta minus theta 0. So looking at these equations, we have this and this, and we have acceleration, we need time. This first one's going to be simplest. The initial angular velocity is 0, so that means time is just, well, let me show more steps. So divide each side by alpha, t equals omega over alpha. That's omega final. And it's 5.2 radians per second over 4.0 radians per second squared. That comes out to 1.3 seconds. So let's look at another situation. You're running a blender. The blades are whirling with an angular velocity of 375 radians per second when the puree button is pushed in. When the blend button is pushed in, the blades accelerate and reach a greater angular velocity after the blades have rotated through an angular displacement of 44 radians. That is delta theta. And this would be omega naught. The angular acceleration has a value of 1740 radians per second squared. That is alpha. Find the angular velocity of the blades, or omega f. So let's write all this stuff down. Theta, theta naught, theta final, omega naught, omega final, alpha t equals, well, let's set this equal to 0. That seems like the rational thing to do. We know what delta theta is. We don't know what the original theta is. It turns out it doesn't matter. Let's just set it equal to 0. and the angular displacement at the end is 44.0 radians. So delta theta is the same as final theta. The original angular velocity is 375 radians per second, and the final velocity, we don't know that. That's what we're after. Do we have? Yes, we have alpha, 1740 radians per second squared. Okay. So now if we, where did I put it? If we look back to our kinematic equations, we have theta final and theta initial, so we can use these equations if we want. We have the original, the initial velocity, angular velocity, and we need to find the final velocity. We don't have the time, so unfortunately that knocks these two equations out. And this equation. So all we're left with is this one kinematic equation here where we have this, we have this, we have this. We have this, we need to find that. We have acceleration and we have displacement. Okay, so omega f squared equals omega naught squared plus 2 alpha theta minus theta 0. No, that equals 0. Nothing else zeroes out. So then solving the equation is just taking the square root of each side. Okay, and now we can plug in 375 radians per second squared plus 2 times 1740 radians per second squared times 44.0 radians. And the final angular velocity thus is 542 radians per second. Centrifuge. It operates at an angular speed of 420 radians per second. Will that be final? Okay, so we're increasing. So I'm going to call this omega naught. In 5 seconds, that's delta t. This speed increases to the final angular velocity of omega f. Determine the angle, which is delta theta, through which the rotor turns. What is the magnitude of the angular acceleration? Okay, so let's part A. First thing we do, list our variables as usual. We don't know what the original, what the original angle is. We'll just call that 0. And we don't know what the final is going to be. We know what the initial angular velocity is. It's 420 radians per second. And we know what the final is, which is 1420 radians per second. And let's see. We don't have the angular acceleration, but we do have the time, 5.00 seconds. And we want to know what is the angle through which it rotates. So we're looking at angular displacement. Well, if you look at your kinematic equations, I think this one is the easiest one. 1/2 omega plus omega final times t. And we can expand this like theta minus theta 0 equals 1/2 omega naught plus omega f times t. So this goes to 0. And we're just looking at the final angle theta. Again, you know, this is the general way of saying it. You could say the theta final is the same as delta theta, but this is more general because you know you could start at some angular displacement in reference to a 0 angle line, in which case you'd have to do it like this. Anyways, that equals 1/2 the original angular velocity plus the final angular velocity times 5.00 seconds. When you do all that math, you get 4,600, whoops, it's a comma, not a 6, radians. Now B says, what is the magnitude of the angular acceleration? Okay, we can do that. If we go back to our kinematic equations, this is, I believe, the easiest one. We have these two things, so let's subtract the initial angular velocity from each side. And now let's divide each side by alpha. So t then is just omega minus omega naught over alpha, which equals 1420 radians per second minus 420 radians per second, all over, oh, excuse me, solve for the wrong thing here. Over t. So alpha is what we're solving for, and t is in the denominator. Okay, so subtract these two. It's going to be 1,000 over 5, and your result is 200 radians per second squared. All right. All right, our next problem is literally a walk in the park. For those of you that like puns. You've got two, I really like this problem because it makes you be a little bit creative and have to think a little bit. So you've got two people that are walking the same place around a circular path. So let's draw the circular path. One walks with an angular speed of, I'll put omega 1 here, 1.7 times 10 to the negative third radians per second. And the other with an angular speed, this is omega 2, in the opposite direction, so it's negative 3.4 times 10 to the negative third radians per second. How much time passes before they meet? That is delta t. Okay, so we're going to have to think a little bit, and you know, what is the constraint on this problem? Well, this person walks some distance, we'll call that, and he's walking in the negative direction, so we'll call this theta 2, and the other person walks in that direction, and we'll call that theta 1. So we know theta 1 plus theta 2 equals a full revolution, one revolution, which equals, well, ran out of space, 2 pi radians. However, this is going to be a negative angular displacement, and this is going to be a positive angular displacement. So I can't really say one plus the other. I'm going to have to say the absolute value of each. So theta 1 plus theta 2 equals 2 pi radians. Okay? Seems like the color in this video is a little washed out. Anyways, if we look at our kinematic equations, we have that one that is theta minus theta, well, theta final minus theta initial equals omega initial t plus 1/2 alpha t squared. Well, there's no mention of alpha. It looks like they're not accelerating at all. They're moving at the same speed, so this goes to 0. And we can also say they start at the 0 position. So then, theta 1 equals omega 1 t, and theta 2 equals omega 2 t. So we can plug those in over here to this condition. So that means omega 1 t plus omega 2 t, whoops, not absolute value of each of those, is equal to 2 pi radians. That's because if I take the absolute value of each one of these, I take the absolute value of each side. Well, I can pull t out of both of those because we know t is going to be positive. So the absolute value bars don't matter for t. So that means the absolute value of omega 1 plus the absolute value of omega 2 equals 2 pi radians. Divide each side by omega 1 plus omega 2, absolute value, omega 1 plus omega 2, absolute value. And so t now is equal to 2 pi radians over omega 1 plus omega 2 absolute value. So that equals 2 pi radians over omega 1, which is 1.7 times 10 to the negative third radians per second, plus negative 3.4 times 10 to the negative third radians per second. So that's why the absolute value is in there, to get rid of that negative sign there. I think that lighting's a little better now. Time then is equal to 1,230 seconds or 20.5 minutes. All right, helicopter blades. We have helicopter blades rotating at an average speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second squared and the question relates to a point, to point 1 here, which is 3.0 meters on the blade. They want us to find the magnitude of the tangential speed and the magnitude of the tangential acceleration. So first of all, let's write down the stuff that we know. You probably see already that we're going to have to involve some unit conversions. So let's just write these things down. Theta final, omega 0, why did I draw that line there? Omega final, alpha t. So we can call omega 0, 0. This we don't know, but we probably don't care. We don't know this, we don't know that. We do know the angular acceleration is 1.3 revolutions per second squared. Oh, I'm sorry. The initial angular velocity is right there. So that's 6.50 revolutions per second. It's acted upon by this acceleration. We don't know what the final velocity is because there is no final point in this problem. But let's take this angular velocity and convert that from revolutions to radians. And we know there are, in one revolution, there are 2 pi radians. So that means our angular velocity originally is 40.8 radians per second. Do the exact same thing for this was velocity. We'll do the exact same thing for acceleration. And our answer is 8.17 radians per second squared. We don't have time, but we do have, oh, well, I'll call that R1 for 0.1. It's 3.0 meters. So the first part of the question asks for what is the tangential speed or linear speed or transverse speed. These are all the same thing. V equals R omega, if you remember that from class. So this is in meters per second, this is in meters, this is in radians per second, which radians are kind of unitless, so meters per second, meters per second. We have R, 3.0 meters, and we have omega, which is 40.8 radians per second. That means our tangential velocity is 122 meters per second. So that is the linear velocity. So it's moving around in the circle. The linear velocity tangential to the circle is that right there. Part B asks for what is the tangential acceleration. I guess I should put subscript t's there. Although you know the difference between tangential and angular because one is Greek letter, one is a Latin letter. But anyways, that is R alpha, so 3.0 meters times 1.3. That's revolutions. We want radians. 8.17 radians per second squared. AT is then equal to 24.5 meters per second squared. You could say this problem is a whirl of fun. Okay, going to a discus thrower now. The discus starts from rest. The thrower accelerates the discus to a final angular speed. Well, go ahead and put omega f there. In a time, delta t, before releasing it. During the acceleration, the discus moves in a circular arc of radius just under a meter. So if we look at the image, the radius would be like this. Find the magnitude of the total acceleration at the final position. Well, this image here does a lot to solve the problem for you already. You may not have a diagram like this on the test, so beware. Because this shows you that there is a tangential acceleration and there is a centripetal acceleration. Because he's keeping the object in a circle, which is a kind of transverse acceleration because it's working in the straight lines xy plane. So this is a linear acceleration, and this is also a linear acceleration because he's at that point in time he's increasing the speed with which the object is moving in a linear fashion. So we have to find the vector sum of those two, and that will be the total acceleration. And here the diagram is drawn for you. The centripetal acceleration, the transverse acceleration, and or tangent acceleration, I guess tangential acceleration you could say, and this is the total linear acceleration. All right, so let's do this. We have, let's see, angular speed before releasing. So if we look at our, well, let's write our variables down. 0, the final theta we don't know. The original initial velocity is, starting from rest, so that equals 0. And the final angular velocity equals plus 15.0 radians per second. Delta t is 0.270 seconds. And radius equals 0.810 meters. And we want to find, well, we need to find alpha in order to find tangential acceleration down here. And then we can also find centripetal acceleration from the velocity at that point. So looking at our kinematic equations, omega final equals omega initial plus alpha t. We know that equals 0. Divide each side by t. Yeah, and so then alpha is just equal to omega f over t. Well, how do we find the tangential acceleration? Well, at is just equals r alpha. So at is equal to r omega f over t. So that's one part of the problem. We could go ahead and throw in numbers if you like. Um, 0.810 meters times plus 15.0 rad per second over time, 0.270 seconds. So AT is equal to 45 meters per second. Okay, so now we also have to find in centripetal acceleration, which we know is equal to v squared over r. So v squared, that's linear velocity. If you remember, v is equal to r omega. So that equals to r omega squared over r, which is r omega squared. And that's the final velocity at that point, remember? Because the centripetal acceleration is changing because he's increasing the speed over time. So that is equal to 0.810 meters times omega f, which is plus 15.0 rad per second, all that squared. So the centripetal acceleration is equal to 182 meters per second. So now we have to just find that the total acceleration is equal to the square root of the centripetal acceleration squared plus the tangential acceleration squared. These two things. Actually, that was well, that's the magnitude, excuse me. It's equal to the square root of 182 meters per second squared plus 45 meters per second squared, which then equals 187 meters per second squared. Okay, the next problem involves an accelerating car. So the car starts from rest. So we could say that the angular velocity in the beginning equals 0. The translational velocity also equals 0. But we're mostly dealing with angular stuff, so let's put it in terms of angular. It accelerates for a delta t time interval of 20 seconds with a constant linear acceleration of this, 0.800 meters per second squared. The radius of the tires is a third of a meter, a little less than a third. What is the angle through which each wheel has rotated? This is where we're mixing in angular components and linear components. And we're using this relationship to get there. We know that the distance traveled by the center of the wheel is equal to that arc length that comes in contact with the road. D equals S. So let's write down the stuff we know. Theta 0 equals 0. Theta final equals, we don't know about that. Omega 0 equals 0. Omega final, we don't know about that either. Alpha, we don't really know about that. Time, we know, is equal to 20.0 seconds. And translational acceleration is equal to 0.800 meters per second squared. So how do we relate these variables? Well, the translational and the rotational variables. So do you remember how the translational acceleration, or I should say transverse or linear acceleration, let's put it that way, is equal to r omega? Okay, or we could say omega is equal to at over r. Why do we need to know that? Well, I'll show you. Because starting with going back to our kinematic equations, the displacement, angular displacement, is equal to the angular velocity in the beginning times time plus 1/2 alpha t squared. Well, we remember that it was starting from rest, so that goes to 0. Theta naught is equal to 0, so theta is equal to 1/2 alpha t squared. Well, we don't have alpha, but we do have these other things, so we can put that in there and say 1/2 at over r. The linear velocity over r times time squared. So that gives us the, what is the angle through which each wheel has rotated? That gives it to us. So theta is equal to 1/2 at 0.800 meters per second squared over the radius. I forgot to write the radius down there, 0.330 meters, times time squared, which is 20.0 seconds squared. When you do that calculation, you come up with, well, one thing that, you know what, this should be negative. This should be a negative angular acceleration, because as the car is going forward, the tire is going counterclockwise. So that's a little bit of a pain. I'm going to put in the negative there, and this is going to take me to negative 485 radians. Now the thing is, though, I could just say that I'm looking at the car from the other side. And so if I'm looking at the car from the far side, on the other side of the car than we're looking at in this picture, then the car tires are all going counterclockwise and it would be positive. But either way, it would be fine. Okay, our final problem is we have a large freight train that accelerates from rest. So omega originally is 0, giving it r equals 0.35 meters, giving it 0.35 meter radius wheels and angular acceleration, this is alpha, of that after the wheels have made 200 revolutions, so this is theta final. How far has the train moved down the track? Well, this first part is just let me write down all the stuff we know. Theta 0 equals 0, theta final equals 200 rev, omega 0 equals 0, omega final equals, well, we don't know about that. The angular acceleration is 0.250 rad per second squared. And time is equal to, we don't know that. In A, okay, so the angular displacement is 200 revolutions, and we can multiply that times 2 pi rad per revolution, which gives us 400 pi rad. So that's the angular displacement. Well, now we just need to know that the arc length traveled by that is equal to r times theta, and that arc length is equal to x. Because if we go back to, where is it? If we go back to this little drawing here, the arc length s is equal to the distance that the middle of the wheel moves, d equals s. So actually, I call this d to keep it consistent. So d then is equal to 0.35 meters times the angular displacement, which is 400 times pi radians. And d is then equal to 440 meters. Part B. What are the final angular velocity of the wheels and the linear velocity of the train? Well, now we'll have to use the kinematic equations. So I'll use this equation. Seems to be easiest. Where the original starting point is 0. The initial angular velocity is 0. We have, let's say we have that. So we can just solve it as such. Okay? All I did is took this term away, took that term away, took the square root of each side. The square root of 2 times 0.250 rad per second squared times 400 pi radians. And when we calculate that out, that equals 25.1 radians per second. Now we also, that's one part, we also want the linear velocity of the train. Well, we know from the equation that the linear velocity is equal to just r times the angular velocity. That you see that trend there when you go from linear to angular. Well, when you go from angular to linear, you just multiply r times the angular term and you get the linear term. So this equals, let's see, where are we? What is the radius? Okay. 0.35 meters times 25.1 radians per second. That is going to bring us to 8.77 meters per second. That is the linear velocity of the train, because that's the linear velocity of the wheels.